Okay, so we are back and diving into the peer-to-peer network again. I left off last video having dug into ENR, eNode, and node state a little bit. There's still some stuff to go on in there, but those folders, I think for the time being, we've ticked off. We also looked into simulations, which was just like a testing framework for this peer-to-peer thing that they've got built into their system. So I next kind of want to have a look at, I guess we kind of know now how the structs are built to maintain our lists. But we haven't done actually any like talking to the outside world or anything. And this RLPx, I think, is where I want to look at next. And I was digging into this, like some just internet Googling, and we've got RLPx, Node Discovery Protocol, is how the Ethereum client discovers other peers. And it's based on an overlay maintenance mechanism called Camilla DHT. I haven't seen where Camilla comes into this yet. But yeah, no, Codemlia? Anyway, so let's have a look in RLPx and see what we get. Because we kind of want node discovery, and we kind of want them to like tell us how they find people and put it into this eNode stuff. So I wonder if there's any ENR stuff in here. Nope. And this is quite small, isn't it? There's only two real files. Vim RLPx, which is not very big, and buffer, which is tiny, absolutely tiny. 127. Okay, what do we got? Buffer we might be able to tick off real quick. Buffer has a data and an endpoint. That's it. All it does implements buffering for network reads. But it, okay. They want the buffer slice exposed. So it's just literally like this array of bytes with a little bit of like structuring around it. Reset sets it to nothing. I guess efficiently sets it to nothing. Read finds like X amount of bytes out of it. So if we go from here to N, I guess it is start of buffer to end. Here to N probably. Yeah, okay. Grow the buffer, makes the buffer bigger. Read, write, append zeros. Grow slice. So this is all uninteresting. Cool, good. So we can tick off that. So it's really only one file, which is this RLPx network. Connection is an RLPx network connection. Wraps low-level network connection. The underlying connection should not be used for any other activity when it's wrapped by con. So pretty much this net, you can send messages over, and it's saying don't use it for anything else while you've got this structure built for it. So connection, session state, HMAC. Holds the state. So we've got our new connection, returns a connection, so you pass in, there's not very much there. But that's probably what I'm going to search for to find where this gets used. So we've got some compression stuff, so it's just config config reads a message from the connection. So I'm assuming that puts it into maybe that buffer we were looking at before. Low level passing frames. Writes a message to the connection. So far none of this has actually been like where this guy is saying it's like a discovery protocol, which I guess is discovery. This seems pretty interesting. Cademlia. Each node is associated with an enode ID. We looked at that. We've got an enode ID, which is hashed with SHA-3 to get 256. Oh, interesting. Defines a distance by a Zorn metric. So the distance between two 56-bit numbers is their bitwise exclusive. This is not come up yet. I have heard of this. So they define like buckets and put peers based on their hash. You can compare your hash, I think it is, with their hash by this exclusive OR. And then you sort of go through it and say that this is my distance according to this like exclusive OR. And then you have a bucket for how far away each person is by their distance. So not really like an actual physical distance, it's just like a hash distance between your hash and their hash, I think. To discover a new peer, the Ethereum node chooses itself as target X, looks in its buckets to find 16 nodes closest to the target X, and asks them each to return 16 nodes from their buckets closer to the target. Okay, so it's like efficiently trying to find people through a P2P network. Ping pong, find node and neighbors. We looked at database. Geth stores information in two structures. Long-term database contains information about every node the client has ever seen. Each DB entry contains node entry, IP address, TCP port, blah. Okay. Yeah, here's the last ping, last pong, and a number of times the node failed to respond to a find node message. And we remove if it's older than 1 day. Interesting. Cool. So we dug through that last time. The second, table. I definitely saw that last time. Where was that? Where was it? Inner. Enode, maybe? Was it in one of them? Discover. Table. Okay, so there's a different, they're talking about a second data structure. So we've got our database, which we maintain our pings, pongs, and find node messages, which I didn't know last time, but we knew we were checking how many times they failed. Short-term database called a table. A table is empty when the client reboots, so it lives in memory only. We don't save it, doesn't persist. We've got 256 of these buckets, each can hold 16 entries. And another Ethereum node. So it contains all the same information, but it's just like short term. When it starts up, it has an empty database when it first starts. So like it does persist the database. It knows about 6 hard-coded ones, and then it starts to discover peers, adds them to the database and tables. Interesting. Very interesting. So this table is like a short-term version of the database. So exit this. RLPx, it didn't really get described very well in that. But it seems really low level. Like you have a connection, and that connection is just sending messages between someone. So it's like I pass this connection with like an IP address of or maybe not even that. Maybe it's like, you passing a person's like eNode ID or something. Run recipient negotiate session token on connection. Handle authenticate messages. These are all really, really low level stuff, which I guess makes sense. It's like everything's built on top of this. Share static share secret. So handshaking, so we can encode stuff between each other. Make an authenticated message. So RLPx spec for the last up-to-date version. It's a TCP-based protocol for messaging among nodes. So you establish your capabilities. Current protocol version is 5. Okay, I've got to remember that properly. Everything seems to be 5 at the moment. All cryptographic operations are based on elliptic curve number. The initial handshake. Okay, we connect to the recipient, send it an auth message. The recipient accepts, decrypts, and verifies auth. Generates an auth ACK. Sends it back. No, generates secrets first. And encrypts the encrypted hello message. Initiator receives the auth ACK back. Receives the encrypted frame. Receives and authenticates the first encrypted frame. Sends its first encrypted frame containing an initiator hello message. So recipient sends a hello message, sends its first containing the initiator hello message. Recipient receives that. You authenticated first frame. Initiator receives and authenticates first. So it's just real handshakey stuff like, hi, I exist, talk to me. And like, yes, I understand you exist, I will talk to you, sort of low level stuff. Then they establish capabilities. So the different capabilities is message encoding. So you encode a message with RLP, and then you've got P2P capability. There's hello, disconnect, ping pong. There are 4 messages that can be sent in this capability messaging. Okay, that's less interesting. Dead links everywhere. Alright, so back in here. I don't think we're actually going to find anything in RLPx. I think this is all just like import public key. Yeah, see, it's not really actually anything useful here. So let's do this new connection. We go into P2P and see if we can find where that new con is. it's in transport. Ooh, interesting. In this root folder of the peer-to-peer. So let's look at that then. So this RLPx didn't really do anything super useful, interesting right now, because it's all talking about how to actually send a message to someone. And it's kind of like this RLPx document here is probably more useful for that, because it just tells you how to interact with it. Transport is 5.6 kilobytes, which is not the biggest dial and server are, I guess. But if we go back to this, new RLPx, great. So it just wraps it. We got an RLPx transport. So we'll call that new RLPx, and it's in server. Cool. So it looks like we are gonna dive into server then. This isn't very big at all. Transport is just a wrapper for that RLPx. So it just creates a new one, I guess. And then it just manages its lifetime, I guess. So we've got an RLP transport structure, which has got our RLPx connection. And there's a, no, that's not it. Bytes buffer is different. So we create a new one, we can read a message from that RLPx connection. And in it, we drag out the message somehow. Connection.read gives the code data wire size. And error. And if error is nil, yell about it. If error equals, if does not equal nil, you return it here. But if error doesn't, it is nil. Copy bytes from data into data. And then craft this new message. So I wonder where message is defined. Probably in this folder. And we create a receive dat. We got our code, which I assume is these hello disconnect ping and pong messages. Maybe, or maybe not. Write message is the same thing, but the opposite, I guess. So they go into the buffer, clear it out, and then we copy into that buffer whatever the payload we've defined is. So we're working with these message structures, and it's like coming in and out. So this RLP transport structure, it kind of just converts into and out of this message structure. So I think those codes might be those 4 ones we defined, but unsure at this time. Set a deadline, set metrics, and then close the connection if we can't use it or want to get rid of it. Do handshake, do protocol handshake. So I guess on start we have to do the handshakes. So this wraps it. So this is just like in that RLPx. In here we've got all like the functions to do stuff. So like handshake. There's a function, do a handshake. But we don't actually call it in there, we do it in here. Like we wrap it all in this like structure to hold it. And then we call them from here, I guess. If message code equals handshake message, does not equal handshake message. I didn't think there was a handshake in there. this is. So this has got to be separate. Maybe those codes aren't here. Read protocol handshake, write protocol handshake. Okay, cool. So this is all just a wrapper, and the meat of it's going to be in this server, I guess. So let's look into that. Server is here. And we've got new connection. Where was it? New RLPx, isn't it? There. So we've got a transport. And this is all going to be on the new start server. Ooh, interesting. So this is probably going to be a structure that wraps that that RLPx structure, and then this server structure probably lives on the blockchain structure. There's another connection on. We have a connection with an node, and then we've got this one to actually talk to them, so we know who the node is, the name and capabilities. So they do a protocol, build this name. Okay, so that's sort of going to be interesting. So that server, peer-to-peer.server, I assume lives on a node. Let's find if there's a new server. Maybe not. Run, interesting. Start and run's different. So it doesn't have a new. So what this is going to be is in node, vim node. Nope. Here we go. So in our node structure, which gets started up, we have this peer-to-peer server here on our structure. And in it, we call that server occasionally. We're passing a config for the peer-to-peer into this. And that's when we create it. So we do a new server when we do a new node. And then we call things like node config, node key. Now these are all configs. So we set up our configs, lots of configs there. Nope. Then we call start when we call this open endpoints thing. So we've got a name, which I assume is enode or whatever it is. Call start, stop. I think that's it. We're just calling start is what we're doing. We're initializing it with the base structure when we get a node, and then we're calling start. So if we go back up to the top here, there's a config stuff, which has probably got some useful things in it when we actually understand what it does. But this server just exists. We call a new server when we call a new node. And then ntab is discover UDP v4. Discover v5 is there. That might be useful later. It's going to be something similar. But this is all just like big big structure that maintains everything to do with peer-to-peer. So we've got our connection there again. We looked at transport interface, string from a connection. Okay, these are all connection stuff. Here's our server. So let's look at start then. When we start the server, so we built the node and then it says open endpoints. So there'll be like a peer-to-peer started run-ins at the very start when you turn on Geth. So yeah, it locks it, which is uninteresting stuff. If the server's running, spits some errors. We go find the log, so we can write logs to it. I guess it's just going to be like a buffer, like input-output buffer or something, and it could be a file or it could be like a screen. Set our clocks. If server no dial and listen address equals 0. Cool, so you can disable the peer-to-peer server if you're doing stuff. Interesting. Server has a private key, you must have it. I'm not sure where it gets that private key, probably from that config. If we don't have the transport, we create our new RLPx transport. New transport. It must have been an old transport at some point. Never renamed it. Never renamed it new. A listen function, which is just a network.listen. So that's high level 2. So net.listen. Maybe there's another net in here. Net util. Yeah, okay, so this is not it. These are just like high level functions describing who's like a public address. Okay, so all these are like locked addresses. And if you have an address range in this, then you know what it's going to be. So you can kind of search, like if it's in this range. Oh, maybe. I'm thinking something different actually. So it's just saying don't accept connections from these, I guess. This stuff is not interesting. Uninteresting goes away. So we got back to our server. So we've created our new transport here. It's under this server structure. Set up listening, set up local node. Probably something we need to look at first. Set up listening, set up discovery. Set up dial scheduler. So I think here, this is where the logic is. From between like here to here. The server is setting up everything. It's saying run. So set up local node is the first thing it does, which is this first function here, which has a little bit going on in it. And then we've got set up listening, set up discovery. Set up discovery was underneath it as well. But let's start this. So we have our public key for us, and we get a pub key converted into from its bytes into an actual like pub key that we can do stuff with. We define our handshake. We've got a server name. I don't know what these names are yet. We've got a base, so we've got a protocol handshake structure, which lives on our server permanently. And I guess it just sends it out to everyone, which kind of makes sense. When you got a peer coming in, they say, send me your details, and you just send that structure directly to them. So our handshake capabilities, we go over all the server protocols and add it there, which I think is probably in this like where the capabilities messaging. Capability is identified by a short ASCII name and a version number. Max 8 characters and a version number. So that gets sends in a hello message when we do RLPx stuff. So we're building a handshake, sorting it. Yay, so it's in order. Enode open database. So we were looking at that before. So we've got our database, it lives here. And again, passed in by this server node server config, which got passed into the node originally. Then we save our node database. This is really just initial stuff. So node DB is an enode database. Is that exactly what we were looking at? Enode database, yeah, it was. Cool, so that's where our long-term stuff is getting served. Got a new local node. So we define ourself as a local node on it. And that's going to be a ENR, is it? No, local node. Local node is this. So local node, I assume, is the exact same thing as a normal node, but we just know that it's us we're referring to. It's probably got some extra stuff. Produces the signed node record of a local node. Cool. So go through our protocols, and they've got attributes. Each protocol has an attribute, and on that local node we set the attributes. Then depending on the NAT, if we have, okay, so we want to get our external IP. And if we have to go through a NAT, it might block us. So if it does, we might have to ask the router for it. And that's it. It kind of sets up our IP. So they have to do a little bit of roundabout to get that. Is that also in here? Is there a NAT? Yes. So that's what this is going to be all about. Is like, how do we get our IP? And I think that's just like it's not trivial to get that sometimes. So back on our server, we got through that first one. That setup local node, cool, setup. If we don't have a listen address, we call setup listening. So So we have a listener, which is just going to be, we've got a port, a peer-to-peer port that messages can come in on. And when we do get them, that we got to, you know, decode them and send them to the right place. So listen function TCP. I think listen function is just going to be net.listen. So you call net.listen dot Golang net listen. This is literally just to set up like a listener. It's such a redundant word to describe it, but you've got a port. You can talk. People can talk to you on it. Like they can send messages and it's open. Cool. Sets it. Gets the address. Update the local node. Okay, so we've got our local node here. We tell it where we're listening on. And nat.map. So this is just allowing the router to know possibly where to send the messages. And then we go listen loop. So this all sets it off and it just goes off into its own like process. And in this own process, it's just like if it gets a message, it'll pass that message to a channel, I assume, and that channel will be like what to do with the messages when we get it. So this is quite big. What's that? 70 lines. Runs in its own Go routine, accepts inbound connections. We've got max peers. Some more config stuff. And then we go through the work groups. If something comes into slots, so we make channels available for people to send messages in. And that's max pending peers defines how many slots we've got. Wait for slots to be returned on exit. This ensures all connection go routines are down before the listen loop returns. So wait for your peers to like shut down. Cool. So we've got a message possibly coming in, but we don't read anything until we know we've got this slot available. I don't really know what a slot is. It seems like an empty structure. If they're occupied, we can't use it yet. So we wait for one to free up. Then when we do, we do this loop. And this loop is just going to be accept a message, which I think will hold it. Like this will make you wait. So I'm not super like familiar with how this TCP stuff works in Go. But yeah, I think it's just going to say like, hey, look, when we've got a slot available, it sits there and it waits for the listener. if it's not an error, break out of this for loop. And then we take that FD, file descriptor, I guess, and checks this inbound connection. If it doesn't like that, it'll reject it. And then it checks if this remote ID is not nil. If it's not nil, we build ourselves an address from it. And we create this new metered connection, which is going to be that con sort of structure we saw above. We found someone's address and we got like someone sending a message on it. And then we've got to do stuff with it later. So we're calling this setup connection with this FD. Cool. And then we put the slot back. So how many slots does it have? 4. We got these number structs. So we take them out when we get it. So take out a slot. Yeah, cool. What's this new metered connection do? Interesting. CD peer-to-peer, new metered con. It's in dial. That was the next biggest one. Let's not dig into that yet. Slash setup connection. Get me out of this. So runs the handshake. So we've received a connection in and we've got their address and stuff. Dial destination is a pointer to an enode. So we pass nil into this like enode thing, but we do know the file descriptor, which has got whatever this new metered connection dial does. And that's got an address in it. And this inbound connection. So in this setup connection then, what does it do? Runs the handshake. Here we call new transport, which is what our server had, but it's calling it like a function with this file descriptor. If dial destination equals nil, if it does not, yeah. So it does it with a nil, but it just passes it through. No, it doesn't pass it through. It passes the pub key through. Interesting. So whatever this new transport is probably back on that transport thing. But it calls this setup connection using that. Now it creates the connection there and sets the transport on that connection. Then we pass it to here, this connection. Prevent leftover pending connections from entering the handshake. If dial in, figure out the remote public key. If it doesn't have a public key, it fails. We run the RLPx handshake now to get the remote pub key. And we do node from connection. Cool. So there's a bit going on there. Which is where we probably can go back into our RLPx now and see what they do. But possibly want to see what this transport thing is. So on our server, there is a new transport. Is a function that takes a net connection and a transport. New RLPx is called, but it's called without the function being called. So it doesn't actually call that message, it just defines a function. So this is that. So it literally just takes that and puts it into its RLPx new connection. So we've got that. And then we actually call that function with this fd. And that's our new connection here. So what does new transport give us? It gives us an RLP transport, which we have just that RLPx connection on it. What's it do first thing? So it goes into setup connection here, and then it calls that connection and starts doing handshakes. So the first thing it does in RLPx is do encoded handshake, and we pass our private key in so it can do it. So do enc. Wait, what? Why was that not in RLPx? Ac do enc handshake. Oh, it's in transport? Yeah, okay. So we go back here. Do encrypted handshake. Then we actually go onto our deadline, onto our connection, set deadline, and call the handshake. So the first thing we do is set the deadline in RLPx. Which is set read deadline. So this RLPx connection just wraps another net.connection. So we set a deadline on net.connection. Golang net deadline. It just lets you time out. Cool, so they do that for everything. So first thing after that is handshake. So this is what we call. We've got our private key coming in. And it runs initiator and runs recipient, depending on if we've got a dial destination. Cool. So we would have a dial destination. No, because we'll pass in nil in this server, right? In here, this dial destination we'll set as nil here. And this was being set above in this dial dest e node. So these were being set as nil. I've already forgotten where that was set, but in here we know this is nil. So if it's nil, we are the recipient. If we know a dial destination, we want to initiate to them. If we don't know a dial destination, it's because we've received it from someone. So we call run recipient. And there's some initiations. But this run recipient is probably, we've got our listener sitting someone's pinged us, and we call run recipient on it. Run recipient negotiates a session token on connection. It should be called on the listening side. Yeah, okay. So it's the server who has got their listener open, receives a message from someone. We've got our auth message, which has been defined. We read from this connection into the auth message, I assume, using our private key. And that gives us our auth packet. If error does not equal nil, send some errors. Handle auth messages, the next thing we do. Where does this auth packet go though? It gets returned. Cool. So what's handle auth message do then? Imports the remote identity. So we get the public key from the message. No, this isn't helping. But it's got a public key, initiate a public key on it. So we import a public key. I wonder if that's defined here. It is. So it just takes 512 bytes and turns it into a public key on this EC's electric curve something. And then it just gives us this RPub that we can play with. We take a nonce out of the message as well. And we're looking at handshake state, which is a structure I haven't looked at yet. I'm assuming it's important though. So we've got our message and our handshake state, and we are configuring it by setting like who the initiator is. The initiator is nonce. And this remote is who the fuck. Oh no, actually it's not. It's just got this remote and a init nonce, which I assume is just a random number so you know who you're talking to. Generate a random key pair. Then it's got some stuff for testing. So you've got a random private key for this like communication channel, I guess. Static shared secret. So this is really going into like import public key gets called again. Remote random public key. Remote random pub is ECR recover signed message signature. So we take our private key and we get a static shared secret from that. So someone would have sent us a message using that. We get that out. And that token we XOR against the init nonce to give us the signed message. And then passes in some stuff. Okay, this is getting really deep into crypto and it's probably at the edge of my limit of knowledge, but it's handshaking. Handshaking, setting up an encrypted key for the two people who are messaging. Cool. We'll be back in here. Do encrypted handshake. So we run the recipient and it sets up this H. Where's H get defined? Handshake state. Here we go. So it defines a handshake state, which is empty. It's got some secrets for this connection. The connection then inits with secrets. And then we've got the session. Cool. So we have this connection and then it just links to this handshake state through this write buffer and read buffer. Then it returns the secrets of the remote. Where'd that get set? Gets set in one of these, I guess. Cool. So handshake gets called. Great times. Done here. And we get our remote public key back from that, which was just looked at just then. And we take that public key from our handshake. We've done that. And we make a node out of it. Node from connection. And then that's our node, enode new version 4. We just take our public key, the IP address, port and port. So this is just everything we need to generate that enode structure. Cool. So we had this up last time. There's not very much going in. It's got a public key, an IP, and 2 ports. So it just makes that. So we make our node, and we save that in our wherever we were before. Here, right above it. So we did handshake. We generate our node. We then log. We do some logging. Checkpoint post handshake. So it's saving some state, I guess. So we are passing. Okay, cool. So it just allows people to hook into it when that happens, I guess. It sends a message and says, hey, look guys, we've just had a connection. Is anyone listening? And then it passes in that connection right there to this channel. Do the capability negotiation handshake. So do protocol handshake, PHS. Do proto handshake. And that's something that our connection has defined. Maybe it's here. Do protocol handshake. Cool. Writing a handshake happens concurrently. We prefer returning. So we got our RLPx. And that gets a hello message. It does authentication. then we do our protocol handshake, which is after authentication. Is that what it said? Auth message, auth message, auth message. This is probably the handshake. So we're going to send a hello message now. We do protocol handshake and we pass in our protocol handshake, which we defined at the start. Server.rhandshake. Which is literally just base protocol version, our name, and our public key. So we send that to do protocol handshake. Do protocol handshake takes that and sends it in its own thread. And it sends it with this T. What does T mean in this case? It's this transport. So we call send with this as the parameter, and our handshake message is there. Where's this handshake message defined then? I have no idea where that's defined. In peer, it's just a empty. Interesting, because that's what this was saying, wasn't it? In our handshake message, after the initial handshake, both sides must send either a hello or disconnect. I thought this hello message is the handshake. No, initial handshake is before this, possibly. Interesting. Okay, so we've got 0 bytes being sent here, so we send over our transport our protocol handshake with the 0 saying we want to do it, and that goes out into its own thread. And we read protocol handshake, which probably makes it wait there. Return nil error if error does not equal nil. If their protocol supports snappy encoding, upgrade immediately. Cool. So what is send then? Not defined here. P2P. Message has a send. What's in message then? So we write an RLP encoded message with the given code. So we've got a message writer, which is our connection, and that's got this function called write message to it. So our connection just allows us to write a message to it. We pass in our code, which is 0, 0, and the data, which is our handshake message. So it encodes that data into just bytes, I guess. It comes out here with a size. And then you pass that payload in with the size and just create this message and then call him write message on it. Cool. So which is back in here, I guess. It's actually just calling this. Which copies it to the buffer, writes to the connection. So it literally just fires out to the abyss. So read protocol handshake as underneath it, easy. So we're going to read, write, read message. So is message reader defined here as well? It's in message as well. And this is an interface called read message. Read message. If there's a message there, then pass the back. So I think that actually will wait for it there. So it waits for the handshake to come back. At that point, we get their handshake. If their .version has Snappy Protocol version, then we immediately set this connection to have it. So we send everything straight for it. So do protocol handshake returns their handshake here. So if we don't have their ID, this connection we've already established at the start what their ID is. Then we look at what the handshake says, and if that ID that's in the handshake doesn't match up to what we've got, then we get in it for something weird and we just go dump it. We set our capabilities and our name, so it's establishing more stuff. Got another checkpoint, which is just going to be like allow for callbacks and stuff when we get a peer or something. And then we return it nil if it's fine, which is all under setup connection, which is all under this setup connection. Is that here we found it? Is this in the listen loop? Yeah. So listen loop sets up the connection and then gives us slots back. And then it just keeps doing that. So that's all it does. It sort of gets these handshaking messages. And it keeps this table with all our connections. No, it creates a connection. But what does it do with that connection? Interesting. I don't know. think it does nothing. I think at some point this setup connection must save it to our like table, or it must save it to our database somewhere. So it must be in this like checkpoint add peer. Cool. So yeah, this is going to be where we're looking at next. So when we are running the server, I don't know when our server gets called, like to say that. We have messages coming into those channels. So like add trusted peer is a flag, remove trusted is something else you could call from command line, I guess. Checkpoint post handshake. Connection has passed the encrypted handshake, so the remote identity is known, but it hasn't yet been verified. If we have that as a trusted connection, we do post handshake checks. Interesting. And then once we have add peer, we do this add peer checks. Then we call launch peer. Interesting. So let's look at this post handshake checks. Let's see what it does. It's just going to look at it and go like, cool. So yeah, if we have too many peers, if it is a trusted connection and the length of peers is greater than max, return discover too many peers. Same deal. If it's above max inbound connections, too many peers. If we've already got it in our peers list, don't know where peers is defined. Oh, it comes in here. A map of eNode IDs to peers. We've got it already connected. If the ID equals ourselves, disk self, otherwise nil. So nil is good. Continue. Where is this peers defined then? Because that seems to be like a pretty important structure. This is a map of eNode IDs to peers that's defined in this run loop. Is peer defined in here? Peer. Peers. Not by the look of it. P2P ACK. Oh, there's a peer file. So in this peer file, we've got peers. I really want to like get this linked to like that, either that table structure or our database. Like as an end, we've got this peer structure here, and it has a connection. We've got some new peers, IDs, nodes. These are all great. These are all great things, but they're identical to what that other one did. We've got full name, capabilities, running capabilities, remote address, disconnect. Give me a database. Where we got? New peer. DB. No DB. Table. No table. Ah, bugger. So this peer is not linked to our like table yet, or to our database. Start running protocols. But maybe that's right. Maybe we don't want to do that just yet. Maybe we pass this peer to something. So in our server, we've got this run loop. Listeners have come in. They're doing handshakes. Post handshake, this gets called. Connection continue. I guess on that connection, if there's an error that goes on this, then it stops immediately. Checkpoint add peer. So we've got add peer checks. Launch peer. Peers, we add this peer to our map. And our dial scheduler, we have a peer added. So add peer checks. Doesn't actually do that much. It just makes sure that it's got some protocols defined, checks what matches up with ours, do post handshake checks, repeat the post handshake checks since the peer set might have changed. Okay, that's not much going on there. So we do our checks, then we call launch peer. And we return our peer. We call new peer with our connection and our server protocols. And then we call run peer in its own thread. So server peer feed, send peer event, remote requested, announce the disconnect. So we've got a place to delete it when everything goes, so we know how to delete all our peer connections. Peer feed.send. What's a peer feed then? Not in there. Server.peer feed is an event feed. No, not where I want to be. So we send a message that we've got a peer added. I think that's probably where things are going to be. Run the main loop of the peer. Cool. Peer. Run. Here we go. So we run this for every peer we get. Once we're connected, we have this loop that goes over in its own thread. We've got a read loop and a ping loop. They get called in their own threads. Then we start all the protocols. We loop over for an error or a disconnect. And then when that does, we close this connection, return remote requested. Is that? But that doesn't come back. So this sits in its loop. And it goes boop, 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 boop. So it kind of just hangs here. When it returns from this, it means that something's disconnected or someone's told it. So then we start doing things like drop the peer, send peer drop event. So up here then, we've got this main loop. But what's actually happening is this read loop and this ping loop are happening over to the side. And then if stuff comes in from there, they go into these channels. So up here, we've got a read loop. And then we just forever call this loop saying we read the message. So it sort of sits there until we get a message from them. And then ping loop sets a timer, new timer. If the ping comes back, then we send a ping message to up here. Send items, ping message. Send items. And where are you defined? In message. Which is going to be send, same as send. Write an RLP with the given code and data element. And it just calls send. Cool. So that's what we have. We get a peer, and then once we got a peer in our list, we start calling things like wait for a message from them, and also send pings semi-regularly to make sure they're alive. And then we call ping.reset on them. Another reset timer. If we get a ping message back, I assume it starts calling the other things. But I haven't linked that yet. I haven't linked it to our database. But I think I might call it there. This is had a lot going on in it, and we're sort of getting deep into it, and kind of want to keep following this. But I will save that for the next video. Cheers, guys.